Hello, everyone. Welcome to VaporTech's High Performance Functional PVD webinar. My name is O.C. Gabriel. I'll be your moderator today. Augusto Kunrath, our R&D manager, will be presenting this webinar. This will be a 1-hour webinar with a 40-minute presentation followed by a Q&A session. To ask a question, please type it into the Q&A. The Q&A button is in your Zoom ribbon. So I'm excited to introduce you to your presenter. VaporTech R&D Manager Augusto Kunrath has more than 25 years of R&D experience. He's worked on coatings and surface engineering solutions for a lot of different applications. He has degrees in mechanical engineering and material science, and he's published a number of peer-reviewed technical publications. Over to you, Augusto.
All right, thank you, Osi. I hope you all can hear me all that well. Good day to all, and thanks for attending. So let's get started. So just the topics that we're going to be talking about today, I'm going to give you a quick overview, some applications, substrates, and for those that are not familiar with that term, substrates is any material, any part or components that you have is to be coated. Some of the deposition processes, we're not going to go in detail on that. There's a separate webinar where we talk at length on the processes that are used. And even though we call performance coatings and there's different types of applications and functionalities, we're going to focus a little bit more on hard coatings. So moving on, overview. And one thing that comes to mind when we're talking about coatings, are coatings an afterthought? And what I mean by that is a lot of that was developed initially was that in designing a component or designing a tool, people were more concerned about the material, the bulk material that was used for it. And then when coatings came into becoming well-known and used for several applications, people would just apply that on top of the substrate, on top of the part. Nowadays, we can be a little bit more thoughtful about that in a sense that you can design the entire structure. You can select the material knowing that you're going to apply a coating on top of that. And that's quite important. One thing that comes to mind when you ask, when is that coming into play? For instance, if you have components that have a high tolerance or very tight tolerances, I should say, you must be aware that the dimensions of the coating, will add to the dimensions of the part. And therefore, when you prepare your substrate, when you prepare your tool or you prepare your component, you have to take that into account. So just have that in mind. Other question that comes to mind is why coatings, right? Why not just make the entire part out of the material that you have the coatings to? So it's such a because the properties of this coating are so much better for that application. Well, number one is availability. Some of these coatings are not necessarily available in bulk form in nature or even synthetic. It's not as easy to produce them, even if it were. And in some cases, it is. It's possible to sinter powders of some of these coatings that you have, materials of the coatings. The cost would be pretty high. Fabrication limitations as well, the shape, the size of those parts. And of course, there's application requirements. What I mean by that is, although the coating itself has adds to the properties of the part or make those parts superior, have superior properties compared to those without the coating, you still may need other properties that come with the substrate itself, meaning toughness, for instance. And for those that are not familiar with that term, toughness is the ability of the material to submit it to impact or, if there's a crack in the place, it's stopping that crack. So it's not necessarily hardness. Toughness is a little bit different from that. Moving on. Even though we're going to be talking about hard coatings, I'd just like to give you an overview of how complex this whole thing can be and how many different properties you can change or you can add to your substrate. You can have things such as a decorative coating that has heat resistance. Example, for instance, exhaust in motorcycles. So that's one example where you like to have a nice color, but at the same time, you need heat resistance just because of the environment that that coating is submitted to. Decorative and easy clean. You can think of plumbing products. You can think of hardware for doors and windows and stuff like that. You can have corrosion resistance and antimicrobial. There's some push to create coatings that are pesticides that can kill bacteria. At the same time, if you apply that to touch surfaces, such as doorknobs and stuff like that, you'd like to have corrosion resistance as well. Just one more example, we can move on. Hardness and oxidation resistance, really important. If you have a tool that as it's used is the temperature rises because of friction, contact pressure and so on and so forth, and that is not protected by an inert gas, for instance, which is really rare, you would have to have that tool to be protected against oxidation. So all of those things is when you talk about performance coatings, you normally don't have one particular property that is going to be improved by putting a coating on top of the part. I have some other examples here. This presentation will be available. So, and of course, we're going to be talking about at the end that you have the opportunity to ask questions, but also you can also send emails to us, and we'll be more than happy to address those should you have any specific questions. With regards to performance coatings and functionality, where does that performance, where does the functionality come from? You can have something that is right at the interface of the coating with the environment, in which case you can have low friction, we can call it lubricity, hydrophobic properties, which means that the surface itself, the coating has surface energy such that water beads on top of it. So it's hydrophobic, it's fear of water. Anti-fingerprint, so if you have something that the cosmetic appearance is really important, you don't want to have fingerprints to show up. There are some coatings that help with that kind of property. Reactivity as well, corrosion, oxidation, any reaction that might happen with the environment, be that air or be a solvent, a liquid. Those are all things that happen at the very interface between the coating and the environment. You can also have things that come from the bulk of the coating. And I'm not talking about bulk of the part, just the coating itself. And those are a little bit more obvious. Hardness, for instance, pretty obvious. Permeability, meaning you don't want gases or liquids to go through, diffuse through the coating and reach the substrate. So it's a protection of that substrate. And some, a little bit more on the electronic part, optoelectronic properties, some solar cells, they have the way they function, the way they work, they require that sunlight gets into that coating and split the electron in holes, and that's what makes the electricity run through the material. So those are some two aspects, where is it happening? Is it at the surface or in the bulk? And those are basically what we just talked about. With regards to the functionality, how is it achieved? So this is, again, it's not just the composition, which is the more obvious thing that we associate with the properties of the film. And then I have that on the left-hand side. It can be just a metal. An example of that, you can have titanium being applied to some types of implants. You have carbon, which is diamond-like carbon. You have nitrides, carbides, oxides. What those are is components that include those types of elements with a metal. So what I'm talking about, zirconium nitride, titanium nitride, titanium carbide, and so on and so forth. Those by itself, just the composition itself, will bring some of the properties that we're talking about. But you can add to that by changing how that coating is deposited. So density of the film, grain size, and structure also affect how that material behaves. And finally, the architecture. And what I mean by that, you can have a single layer, right? You can have just that composition. We talked about titanium nitride, I think is the most well-known coating for mechanical applications that I can think of. You can have just the titanium nitride, but you can have multi-layers. In the case, for instance, you can have titanium nitride, titanium nitride again, and so on and so forth. You can have graded layers where you grade one of the elements of your coating, and you can have nanostructure. That basically means that you can have small nanoparticles inside your coating, and that goes with how you deposit that material. So composition, morphology, and architecture. Those are the three main components that add to form the coating that you're going to have. In terms of applications, you're going to find coatings in all walks of life and many different components that you probably have either on you at home, and if you have an implant, you might even have it with you at all times. So consumer products such as faucet pans, knives, firearms, and watches, those they combine a property of wear resistant, corrosion resistance, because if you contact with your water or something like that, but also have to have a decorative application to it. So color is important. Coatings with zirconium, titanium, chrome, nitrides, oxides, and so on and so forth are coatings that you're going to find in those types of products. In the automotive industry, we talked about exhaust pipes, color, heat resistant, abrasion resistance. When I see this metal nitride or metal oxycarbide, the ME stands for metal. It's not necessary that you have different metals. In the case of the oxycarbides, it's a proprietary coating that we have. But in the case of the nitride, MEN, it could be zirconium nitride, chrome nitride, titanium nitride. All of those can be used for most of these applications. Speaker covers or grills. We also have, in that case, is the collar, but at the same time, you have to have some sort of abrasion resistance, a scratch resistance, because inside the automobile, you may be moving around and scratching those. You don't want those to show. So you need some abrasion resistance as well. And more, I think is more intuitive is engine components, right? Where you need hardness, heat resistance, and low coefficient of friction. In that case, some of the more obvious coatings that we have are the standard DLC, tungsten DLC, and chrome nitrides are some coatings that are regularly used as engine components. In the medical industry, you have implants, surgical instruments as well. Obviously, you have to have biocompatibility for the implants and corrosion resistance or some resistance to what's inside your body. As well in surgical components, then you have to have hardness and low friction as well. So titanium nitride, zirconium nitride, and DLC are commonly used in that industry. For food, obviously, as a concern about the components being in contact with fruit juice and some other corrosion environments. So corrosion resistance is important, abrasion resistance. If you're cutting meat or you, again, fruit and all of that, you have to have some resistance to corrosion and abrasion. Chrome nitride and the DLC are two of the coatings that are used regularly. In the energy industry, say oil, gas components, and renewables, try to reduce friction. So the DLC, again, is a good option. There's some applications where you have abrasion, corrosion, and heat resistance that are required. In manufacturing or fabrication, and that's a broader category, I would say. You have machining, die casting, injection molding, punches. So all of those, in general, they have some things in common, but normally what you would expect from those is hardness, oxidation resistance, erosion resistance, and so on. And that has the broader category of coatings that you can apply that I have on the right-hand side. So if you have any questions of any specifics at the end, we're going to put a summary of some of the coatings that are used, and we can go from there with the questions and answers. All right, so going more towards the hard coatings, which are used in tools and mechanical components. So tools that, when we talk about tools here, normally is cutting tools, right? So drills, mills, saw blades, punches that can be used for metal forming, but as well punches that are used, punches and dies that are used to form, for instance, pharmaceutical components such as pills and stuff like that. Punches are used in that kind of environment. Plastic injection molding, again, those are tools that are exposed to high temperatures as corrosion environment and fluctuations in temperature. So coatings that are used in that really expand or increase the life of tools tremendously. Die casting, there are some interesting applications there. Again, it's similar to plastic injection molding. It's a little bit more aggressive because now you have, for instance, aluminum or zinc alloys that are in contact with your tools, and those have to be extremely resistant to that, to the temperature and reaction with those elements. So you can imagine that if you have a high temperature that's used to, in those processes, to have molten forms of those metal alloys, that creates a situation where you could have soldering of those alloys to the tool itself. So all of that has to be taken into account. So it's a very aggressive application. And surgical instruments, so like drills and some other components that are used in surgery and so on and so forth. In terms of components, the more obvious are the automotive engine components. So you have the valve train, you can have transmission components, bearings, gears, and so on and so forth. All of those can benefit from low friction as well as, you know, an additional hardness to prevent premature failure. Here's something else that people sometimes don't think too much about. Substrate requirements or the material that you use to have to put the coatings on top. So for instance, if you have a high temperature application, that material that you use as your substrate, your tool or your component must be able to withstand the heat generating during that operation. What that means is if I have a coating that can withstand or operate at 600 degrees C, and you put that on top of a substrate that can't take that temperature because the heat treatment that was used would be damage that or reduce the mechanical properties of that steel in that case, that doesn't help. You need to have the pair that can operate at those temperatures. So that's something that you have to take into account. For instance, if you have a tool that's going to operate over 600 or 700 degrees C, you cannot use a tool steel. You would have to go to a carbide tool, for instance, right? So that has to be kept in mind. The second I have in there is applications with high contact pressure. What that means is if you have either a cutting tool or even in a gear as well, as you have a high contact pressure, meaning you're really pushing hard against your part or your tool, you have to make sure that the substrate itself is hard enough so there's not excessive deformation of the surface, right? The coating is very, very thin. These coatings that we're talking about here are in the range of 1 to 5, 6 micron, right? So a micrometer, if you take your one stem of hair, that's about 50 micron depending on person to person. So you can imagine that the film that we're putting on top is 10 times thinner than that. Deformation of the substrate can get to a point that you can fracture the coating itself. So the substrate has to have enough hardness to support the coating, right? It's called load bearing capacity. Another one on the right-hand side, suitable surface finish. That's kind of obvious. There's some applications that you need a better or lower roughness. And that's not something, the coatings that we're talking about here, they don't have leveling or a smoothing characteristic to them. They will just replicate what the roughness of the substrate is. So there's no gain there by applying a coating. So the substrate itself has to be at the right roughness before it goes into a chamber for deposition. Another one that we talked quickly about was dimensions and tolerance. Some tools have extremely tight tolerances, and I'm talking about in a few micrometers. So if you are using a tool that has no coating and you now want to go to a situation where you apply a coating on it, you have to take that into account. Make sure that dimensions account for that added thickness that you're going to get with the coating. And last but not least is cleanliness. And this in itself is a huge topic. If you are buying a system, you are now moving into a situation where you're going to have those coatings in-house, right? You have to account for how you're going to clean those parts. And we can talk a little bit more about that. Surface prep. So we talked about what the substrates or the parts have to be like in terms of composition and hardness and mechanical properties. But there's something else that we have to think about. One of them is, for instance, on the very top, I talk about in the case of steels, what the heat treatment is. For those that are metallurgists or mechanical engineers, this should be kind of natural. When you have a tool steel or a high strength steel, most of them go through a heat treatment. And that heat treatment is normally it goes like this. You have a heating and then you quench it in an environment. It can be even in gas itself, in the air. You can quench it in water, oil, and other types of cooling environments. And then you temper that. Tempering is you heat it up again to alleviate some of the stresses of that part. And that tempering temperature is pretty much what will determine the maximum temperature that you can not only process that or have a coating deposit on it, but the application itself afterwards. So when you design your process or you design what your part's going to be, selection of the steel and understanding the metallurgical properties of it are important when it comes to decide as well what coating you're going to put on top of it. Okay, so on the right-hand side, right on top here, you have induction heat treatment of a component, right? Just as an example. Number two, let's avoid some of the thermochemical processes. I put as an example here, black oxide and nitriding. And when I talk about nitriding, I'm basically talking about a salt bath or gas nitriding, such as which uses ammonia. But you can also think in terms of carburizing and some of the other processes. These are case hardening processes in which you diffuse some elements into the material and make that surface. You don't add anything to the surface, you just modify the surface of the material, and that you increase the hardness locally. You're not going to get the same hardness you would have with a coating, but you improve the properties of your part. The problem with those is that those leave some residues and make the surface not ideal for deposition, either by PVD or PECVD, which are deposition processes. The one example that it's okay, it's acceptable is plasma nitriding, and I have an example. The one in the center here is plasma nitriding of some parts. And especially if you have that process happen in the same chamber where you do your PVD or PECVD process after that. This is a much cleaner process. And in that case, you don't have the issues you would have with all the other ones that I was mentioning before, okay? Number three, we're talking about microblasting or media blasting. Many parts, a lot of consumer products and some tools as well go through that process as they are prepared for deposition. In the case of consumer products, it's normally not as stringent, what you need to do in terms of blasting. Case of tools, we're talking about microblasting with a different type of media, not necessarily glass beads or sand, but you tend to gravitate more towards aluminum, very fine powders. And that's used to also clean the surface, remove some of the contamination that you have on top. Carefully be done. It has to be carefully done. Normally you do it at lower pressures than what you would do to just remove, heavy scales or something like that. And you might want to use as well shallow angles, meaning not straight at the part, just put an angle to it to really focus on the surface of the part. If polishing is required, number four, then just make sure that there's no residues on the part itself. And when I talk about that, it's not just the obvious things that you see, such as parts of the polishing wheel itself. Trust me when I say that I've seen that before. Sometimes people are polishing parts that have some channels or small orifices. So you will find some of those hairs or particles from the polishing wheel inside, and that will be detrimental to the process of applying the PVD itself. But also make sure that whatever you use as the abrasive or the paste that you use to do polishing, that's easily removed, right? You can't just polish a part and take it to the PVD or PECVD chamber. You do have to clean it afterwards. And now I have cleaning as the last one, because this is really quite important, all right? Cleaning, no matter what process you're using, if it's an aqueous, water-based, or as a solvent-based process, it's not just selecting the right type of solvent for the type of contamination that you have, but making sure that you have all the steps accounted for in the cleaning process, meaning exposure to that solvent, but as well rinsing and drying, so that you have a part that can have a surface that's free from contamination and ready for PVD or PECVD processing. Again, surface preparation, extremely important. Important for cosmetic coatings, even more important in this case here, right? Of hard coatings and performance coatings. The processes that are normally used for generating hard coatings are PECVD, cathodic arc, and magnetron sputtering. This process, we have a webinar that is specific about those processes, so there's no much that we want to add here. I spent too much time talking about those, but just in general terms, cathodic arc, which is the one in the center here, is one process that uses high current, low voltages, and has a very high deposition rate. You can deposit most of refractory metals and their nitrides, carbides, and oxide. Refractory metals, what I mean by that is just metals that have a high melting point. Okay, so things like zirconium, titanium, chrome, tungsten, etc. In the case of magnetron sputtering, then you can use a wider range of metals and even ceramics and semiconductor materials. It's just that this is a process that's a little bit slower. It has a slightly lower deposition rate, but also it requires an additional energy to create the coatings that you want. Meaning, if you're doing a titanium nitride, chrome nitride, and so on, you may need to apply temperature to your parts, which then limits the number of substrates that you're going to use. But it's a well-known and well-used process as well in the industry for deposition of hard coatings. And last, here on the left-hand side, we talk about PECVD, even though the title of the talk is basically going towards PVD. But most of the DLCs or diamond-like carbon coatings that are used in the industry are done through PECVD process or PACVD process, or even high temperature or thermal CVD processes. And that's just the difference in here is that the two on the right-hand side, the arc and sputtering, are done, the coating is made from a solid target, those that you see in there, a solid material that then sprays those out. And forgive me, the term spray is not really a technical term, it's just to make it easy to understand what's going on. You have those metals coming out of the target, and then they combine with the gas that you're using. That can be nitrogen, oxygen, carbon base, such as methane and acetylene, and then form the coating. And in terms of the PECVD process, your source doesn't have a solid source. You have either gases or liquids that are introduced in the chamber, and they become the coating itself. just to give you an idea what these systems look like, these are some of our systems. These two that you see are basically just arc deposition, different sizes. And we have another system that incorporates you can do all of the three processes that we talked about, cathodic arc, sputtering, and you can do PECVD. Forgive me, in these systems, you can do PECVD as well. So it's arc deposition for the most part, and you can do PECVD. And in this system here, you can do all three. Okay, so now something I already talked about, starting materials. In the case of PVD, you're gonna have normally a metal as a source. Those are called in our industry called targets. So like I said, you can have zirconium, titanium, chrome, tungsten, aluminum, basically any type of material. The limitation is going to be, again, for arc, you have to work with materials that have a higher melting point, and the sputtering, it really doesn't matter all that much. You can use almost anything. With reactive gases, nitrogen, oxygen, methane, and acetylene are the four that are used the most. We always, or for the most part, we're going to have argon as well in the process, but that's not a reactive gas. That's not a gas that's incorporated in the coating. It's important for the process itself, but doesn't get incorporated with the coating that you're putting down. So let's just go through some examples of coatings and properties and what they look like. And again, this presentation is going to be available to you to read in more detail what those properties are. Titanium nitride is the first performance coating that came in vogue in the 70s. And it's, as you can see, has this nice gold color. So it's not just the properties, the mechanical properties that it has. Hardness of 25 gigapascal, that translates to approximately 2,500 Vickers if you're more used to that unit. You can't really relate to Rockwell C, which is the hardness that you normally use for determining hardness of steels and so on for high strength steels. But I can tell you this is much harder than that. Thermal threshold or operation temperature about 500, some information about coefficient of friction. It is a material that's biocompatible, cosmetically appealing, resistant to abrasion, adhesive wear. And I think a lot of the industry owes to the titanium nitride where it is right now because it was quite successful in many, many applications. You can modify that coating by adding carbon as well. That increases the hardness a little bit. It's not as, some of these TiCN or titanium carbon nitrides can't operate as high as the titanium nitride, but not by much, right? It tends to be a really high hard coating. It has good applications for a high pressure machining operation. So if you think of titanium nitride is used in turning and milling and so on and so forth, titanium carbon nitride can also be good on those, but in a high pressure application, in which high pressure means that you're going to have the contact pressure at the surface of the part is pretty high, which is different from one of the other ones. This coating performs quite well. Next, chrome nitride. You see on the top that chrome nitride is not as hard as the other two that we talked about, but it has a higher threshold, temperature threshold at 700 degrees C, and it has excellent toughness. Again, toughness is not necessarily hardness, it's just the ability to withstand impact and stuff like that. So that combined with high oxidation resistance, it can apply it to a number of different applications, all the way from metal forming to exhaust and intake valves in engine components, as well as in the food industry. So it really is used across the board as a hard coating and performance coating, I should say. Zirconium nitride. So this is a coating that is, I think historically is not as used as the titanium nitride, but is a high melting point material, the zirconium is, and high hardness comparable to titanium nitride, a higher threshold, so it can be used at slightly higher temperatures than titanium nitride. Coefficient of friction is it's very similar to titanium nitride, and has some additional characteristics, especially with corrosion resistance. That's one of the things that differentiates zirconium a little bit from the titanium. All right, it's not that it's going to be a much higher performance in many applications, but in some applications, it is superior. So if you have something that, in the case of consumer products, where you have constant exposure to water, salt spray, if you're close to the ocean or something like that, the zirconium is going to perform better than the titanium. In this case, zirconium nitride is on a tool here. It's a punch that's used in the pharmaceutical industry, for instance. And here's the Xerox. This is one of our I wouldn't call proprietary coatings, because you're already using it in some industries. And that, even though it may not have as high a hardness as some of the other coatings we talked about, is still pretty high. It has a pretty decent thermal threshold along the lines with the other ones, and has this nice dark gray to black color that in consumer products, sometimes it's important. And not only that, there's some applications, for instance, in medical instruments, where you want to have a coating that doesn't have much reflectivity, doesn't have much gloss, to prevent or to help a surgeon, for instance, not to be disturbed by reflection of the lights on the instrument that they're using to perform the surgery. So this is quite popular coating as well. In terms of not necessarily PVD, but it's a widely used coating for as hard coatings, as low friction coatings, diamond-like carbon DLC. The DLC is basically one of the forms that you can have carbon. So you have diamond is a form of carbon that it has its properties because the way it connects, how it bonds inside the material, differs from graphite that has a different type of bonding, and then DLC is pretty much a mixture of those. So diamond, for instance, is a really high thermal conductivity material, is transparent. Graphite, and it's very hard and abrasive. Graphite is a low friction coating. It's dark. It has a high electrical conductivity, or relatively, compared to diamond. And DLC has some of those properties of both of those, right? So it's a hard coating, it's lubricious, it is a low friction coating, and finds not only applications as a hard coat, but as well as a cosmetic coating. Here's some examples of what we've used that for. DLC, however, is I wouldn't call it a moniker, but it's a name that's applied to several different types of coatings in the industry. So everything that has carbon in it, and carbon is basically that form, and it has some of the bonding characteristics of the diamond, can be called diamond-like carbon. And the most common one, the simplest one, is just a hydrogenated amorphous carbon, which is this one here on the left-hand side. High wear resistance, high hardness, low friction, used across the board in many different applications. But you can change that by adding either a metal or a non-metal, such as silicon and oxygen. And that changes the characteristics of the coating itself. And we can choose which type of coating we can be used for a specific application. So this first one that we talked about is the more general DLC. You're going to find that in many applications. While one with metal, and that metal can be chrome or can be tungsten, for instance, those have more, they are tougher. They're not maybe as hard as the one we talked about before, but they have a low friction as well as high toughness. So applications in the automotive sometimes use this type of coating. When we apply either silicon or silicon and oxygen to the coating, you have more of a corrosion resistance, is less reactive with the environment. So any application in which you are in contact with hot air or a corrosive material, that be it a liquid or a solid, those are good coatings to have in that application. And just to finalize here, I have this. We don't have to talk to in extensive, but you see the application on the left-hand side, the type of tool and component that you use, the type of substrate and the coatings that normally would be used for those applications. So if you have machining, we talked about mills, drills, turning inserts, and so on. The substrate would be typically the tool steel, M2, W1, and carbides and coatings that are the more typical ones, the titanium nitride, titanium carbon nitride. Just another type of example, for instance, if you go to precision mechanical components, then such as bearings and gears, which are done with high strength steel, then the DLCs tend to be probably the best option for those applications, even though chrome nitride may be used as well. So I'll leave it at that. We are running out of time for the presentation itself, and I want to give it enough time for questions and answers. Please ask away. There's no uninformed question. This is a seminar that's supposed to help you out, from those that have a metallurgical degree to those that are just first time seeing those things. So ask away. Thanks for your attention. Ozzy, I'll start reading the questions. Be prepared to answer in a few minutes.
Okay, great. So as Augusto is preparing to answer your questions, I want to thank you for being here and mention that I'll be emailing you a recording of the webinar in the next few days. And I'll also send in that a link to sign up for our mailing list, which will inform you about future webinars if you're not already on it. I'm also going to share a few files now with more information about our PVD coatings in the chat. I've already added some links as Augusto was talking that are relevant to what he was presenting, and we'll finish with a few more files with some information you may find interesting. Augusto?
Yeah, we have a couple of questions here. So the first one is really good question. What's the primary performance differences between the zirc and the titanium-based nitrides? How much they overlap? And they actually overlap quite a bit. If you compare titanium nitride to a zirconium nitride, they have similar color. Not that that's important for the performance itself of the component of the tool. Titanium nitride historically has been more used in machining applications, while the zirconium nitride goes more towards applications where you need more of resistance to the environment, and I'm talking about corrosion oxidation. So zirconium in that sense is a little bit better. So we're talking about implants, for instance. Zirconium nitride is typically used in implants in the medical industry, titanium nitride to some extent as well, but zirconium is preferred. In the case of machining, titanium nitride seems to have more of a niche in that regard. If I were to decide in terms of the application itself, if I have concerns about corrosion, I probably could gravitate more towards zirconium based. If it's more of hardness and application in cutting tools, titanium probably is the best choice. So it historically has been used more. Next question. And if I didn't answer that to your satisfaction, you're more than welcome to place the question again or be more specific about what you'd like to hear. In your experience, what's the most effective way to clean, remove polishing paste before coating? That's it. That's a great question. It depends a lot on the paste, and sometimes the best is not try to remedy what's being done, but try and use some paste that is easier to clean. Start with solvent is always a good choice. Vapor degreaser sometimes helps, but you may have to actually use mechanical cleaning, meaning manual cleaning, if you have issues with difficult geometries, as you put it, if you have pockets, undercuts, or if this is channels and all of that, you may have to get manual cleaning first before you even go into a degreaser, for instance. But yes, it's not there's no easy answer to that question. Each case is different. like I said before, we found some parts. We work with customers in trying to develop the process. I like to say that we sell the process, the machine goes with it, right? And in doing so, we do test parts for the customer before they commit to a purchase. And we receive these parts from different types of customers. Some of them are quite aware of how these things have to be cleaned, and some of them have no clue, right? And in many cases, there's a lot of residue on those components. We found a lot of polishing wheel debris inside orifices and so on. And it's just unawareness, right? People that are not aware of the need for being careful with the polishing itself. So it's not just the paste, it's the polishing wheel material as well. Next question. DLC is not great corrosion resistance, is that correct? Good question. There's different types of DLC, as we were talking about just a few minutes ago. In some applications, for instance, there are some metal DLCs, and I can't go into too much detail because there's the information that we have feedback as well, that they do not perform as well as when they are in contact with water or some types of water. You see, water as well is a general term for a situation where you may have contaminants in the water that they are the ones causing the corrosion. If you work with more, and I don't know exactly where you're coming from with that, if it's just water that you're talking about, or is corrosion because of high temperature. So I'll give you a general answer to that, and that would be if you gravitate more towards the silicon or silicon oxide, the ones that have a non-metal additive to the coating, then they tend to perform better in those environments, right? Also, does any of your coating equipment have nitriding capability? Not at the moment. That has been, we're studying that situation. Next question, how well can various coatings withstand substrate straining? Well, if you think of by straining, I mean you're talking about deformation of the substrate, right? So if you have a substrate that's going to be deformed, of course, you want to make sure that your coating doesn't break. Let me give you an example. If you have glass, for instance, a sheet of glass that's about 1/4 of an inch thick, and you try and bend it, it's going to get to it doesn't have much tolerance for that kind of strain. You're going to break that. But if you have fiberglass or these optical fibers, and you can bend them quite a bit because they are very thin. So the radius at a specific point of that material is relatively large compared to the thickness of it. So it can resist some of that strain. Coatings are similar, right? But there's a limit. So we have an application in which we work with a customer where there had to be a bend test. And we did have to work with composition and process for that coating in particular to achieve something that was satisfactory, right? But yes, you can change your process, and you can create a coating that can take more of that bending effort, right? The straining or deformation. Hardness and or friction coefficient variable in DLC, yes, you can vary that a little bit, but it's going to be normally in the low end of, if we talk about PVD in general, it's going to be 0.4, 0.5, while we're talking about DLCs, it's not going to be a lower end, 0.1 or even less than that. By adding metals to it, you're going to change that. So yes, like we talked about, a tungsten DLC normally is going to have a lower hardness and a different coefficient of friction from the hydrogenated amorphic carbon, which is the more standard, well-known DLC. Could you give more details about chrome carbon nitride, titanium carbon nitride, same, could reach same lab readings? I'm not sure exactly what the question is. When you tend to incorporate more elements into the coating, in the case of the chrome nitride, the chrome carbon nitride, and titanium carbon nitride, you will change some of the properties of the coating, right? I talk lab as LAB. I assume that's what we're talking about. LAB, as for those that are not aware, there's a color system. Please correct me if I'm wrong. Send another question to correct me if I'm not going in the right direction here. LAB are numbers that define the color of a coating or a material. L, how light or dark it is. A, how red or green. And B, how yellow or blue. Yes, you can change the color by altering the amount of carbon and nitrogen in your coating. The same can be done just with nitrogen, for instance, or if you apply use oxygen or something like that. You can tailor that color to a degree. You can't just go full spectrum of color. But yes, your question, yes, you can change. So for instance, if you start with titanium nitride, you're going to have a gold color, and that gold color can vary, especially in the A and the B, as you change the amount of nitrogen. As soon as you apply carbon in there, you can now migrate to more of a reddish rose gold color up to gray, depending on how much carbon you have in it. Next question is chrome oxy has poor adhesion compared with pure chrome on the metal substrate. Why? Well, it depends on the compatibility of the substrate material that you have with the coating that you're trying to put on top of it. So chrome oxide by itself is a very stable material. Oxides in general are very stable. So maybe it doesn't want to adhere to the substrate that you're putting on. But if you start with a very thin layer of chrome and then migrate and then change the amount of oxygen in your process, you can probably get it to adhere well. So it's more to do with how inert these oxides are, and not wanting to bond with their substrate. Everything about adhesion, when you're talking about coatings, is how clean and how can I put it? How clean and free of oxides, carbides, or any other contamination on the surface, and the nature of the coating that you're trying to put on top of it. If you're trying to put something there without an adhesion layer, which is pretty standard in the industry, you may have adhesion issues. So if you start with chrome and then add chrome oxide afterwards by draining oxygen into the chamber that you're using for PVD, you probably can achieve a better adhesion. You mentioned coatings which can decrease friction. Are there coatings which can increase friction? In general, you would think that you wouldn't want that. But in your case, if you have arc deposited coatings, cathodic arc evaporation is a process that in general, it creates what we call macroparticles, right? And those are slightly bigger globs of materials that come out of the target and deposit on the coating itself. In many applications, if you make thick coatings of those, you have a high population of those microparticles, which then, depending on how it's going to be used, we just wipe them out. They're relatively, I wouldn't say very easy, they'll come out by themselves, but even cloth cleaning, you can remove them. There's always going to be some residual ones, and you can have craters as well from where those microparticles come out. And those would increase the coefficient of friction itself. So when we provide data on those films that are made by cathodic arc evaporation, we tend normally to do that for the coating itself after those are removed. So yes, you could increase the friction a little bit by using a cathodic arc evaporation process of a thicker coating. Very well, I think that was the last question. If you have any other questions, yeah, more than happy to address those by email. If you can send them to VaporTech at some point, they make their way to me or one of the R&D engineers in the group. Lucy, I'll hand it over to you, and thank you all for attending and for the nice questions.
Yeah, thanks again, everyone. And don't forget to look for an email from me, and as well as feel free to download or click on anything that I've put up in the chat.